My topic is particle acceleration, so I want to update you on the progress we've been making in simulating particle acceleration in extreme environments, and the topics that will be, like the themes that will go through this presentation is that larger simulations and more dimensions with more physics usually bring interesting new results. So we have also new simulation tools that are being developed with larger dimensions, larger amount of physics. And I think it's making interesting progress, as I'll try to illustrate in the next slides. So to motivate this, the particle acceleration in general is a very, at the very core of, so to speak, high-energy astrophysics. It shows up both in particles that we observe, such as the cosmic rays, the beautiful spectrum that we observe over many decades, and also through the high-energy radiation, such as here synchrotron light that we observe from various sources, such as supernova remnants and pulsar wind nebulae, and of course the extreme events like a gamma ray burst bring us a lot of high-energy photons. So something over there is accelerating particles quite efficiently, and so to speak, the road from scenarios to observations is paved through the energetic particles. So we need to understand how to make those particles. So far, the efforts in the collaboration have centered on trying to understand both the microphysics of particle acceleration, also trying to apply it to model the objects that we observe. In particular, recently, there's been particularly energized by the observations of ultra-high energy gamma rays, so PeV gamma rays coming from Cygnus X3, which means that the primary accelerated particle, is, which probably a hadron, needed to be even larger energies. So this is a microquasar in the galaxy, and also the detection of 240 eta-electron volt cosmic ray with telescope array, so something even more extreme accelerated, that amazing particle. So again, we're trying to figure out what these things are. The puzzles in this business are still fairly old, and they're still with us, so such as the spectra that we observe, are they universal? So we expect to see e to the minus 2 roughly spectra, and is that the only outcome? Can we see flatter spectra? Just to remind you, if we see flatter spectra, that means that the total energy is not converged, so the energy diverges at the high end. So there must be an upper cutoff. Is minus 2, where you get equal the energy per decade, the only logical outcome? In some cases, we actually observe different spectra, so such as e to the minus 3 in photons in young supernova remnants, which suggests that at least some electrons somewhere are accelerating to in a different way, or at least we observe something with a steeper spectrum. Also, we're interested in what escapes from sources. So cosmic rays that we observe are not the cosmic rays behind the shocks in supernova remnants. They're the cosmic rays that escape from the supernova remnants. So we're interested in the fluxes and spectra of escaping particles. And then, you know, just for cosmic rays, we're interested both in what got us to the PeV range, presumably supernova remnants, and also ultra-high energy cosmic rays, presumably extragalactic sources. What they are is still a big puzzle, and this is one of the main focuses of the collaboration. Also, if we do observe a spectrum, can we distinguish what kind of mechanism accelerated these particles? Is it shock acceleration? Is it some other process? And of course, propagation is also an old and interesting puzzle. So the three topics I will try to cover here, which is were a few recent advances in the research made in the collaboration, are acceleration and reconnection and turbulence, acceleration and shocks, and then modeling of macroscopic sources. So in particular, what we'll discuss is that for reconnection and turbulence, the new insights from three-dimensional simulations that have brought to us more understanding of how particles are accelerated in reconnection, and also simulations with radiation and stirring provide very interesting constraints and very interesting ways of modeling and explaining the old puzzles about observations of coronae of accreting black holes. In shocks, we have made some progress in understanding regimes of particle acceleration in shocks, and scaling the simulations to a new frontier of seeing feedbacks in large-scale simulations. So that's development of new numerical techniques has been very instrumental in that. For the modeling of sources, there are new ideas on how to explain ultra-high energy cosmic rays, how to model accretion corona, and also objects such as pulsars and pulsar wind nebulae, and mergers of neutron stars, which will be discussed later in the meeting. So I just want to bring your attention to two annual review articles that were published by members of the collaboration. One is on reconnection, relativistic reconnection by Lorenzo and Dmitry, and another one is on the origin of ultra-high energy cosmic rays by Noemi and Roger. So they just came out last year, so I highly recommend you check them out. So in terms of the collaboration efforts, we didn't have a single direction of acceleration in the previous term, but we realized that acceleration is kind of studied in all of the subsections of our previous proposal. So we've seen the efforts kind of split between different institutions, and also when they're all collaborative efforts. So a lot of the papers I'll be discussing are collaborations of different combinations of people from different institutions. So for the reconnection and turbulence, the centers have been Columbia, Princeton, and Maryland. For shock acceleration, we've had various combinations of Princeton, Columbia, and Wisconsin. And for macroscopic sources, basically everybody in the collaboration has tried to apply their understanding to astrophysical sources. OK, so I want to emphasize that the progress in this field has been enabled by creating new simulations and new kinds of codes that allow us to address new physics regimes. And SEEX has been sort of enabling and supporting and creating opportunities for creation of new codes or maintenance of old codes. So several codes have been both maintained and developed. So Tristan MP, which is started in Princeton, but now is used in several other institutions. So there is a new version, V2, that was developed by Haik Hakabyan, which is a very different code that has all the radiative effects. And then there is an even newer code, Entity, that includes both radiation and GR and runs on GPUs. So Haik has been very instrumental in leading all of these efforts, and our hats go off to him. He's amazing. Also, we have developed new techniques for modeling MHD-PIC. So there's MHD-PIC code in Athena, and also in Pluto, and also will hopefully be in GPU version of Pluto. So this is work between CETA and maybe Princeton. And also, the members of collaborations have contributed to the development of a relativistic module of Jekyll, which is a Vlasov code. OK, so let's talk about some of the applications. So let's talk about reconnection and acceleration reconnection. So here, this is a simulation of a canonical relativistic reconnection, where you can see the formation of X points and advection of X points towards large plasmoids, collisions of plasmoids, et cetera. So beautiful hierarchical evolution of an unstable current sheet. And the important thing is that the collisionless reconnection in particle and cell simulations shows that reconnection can be very fast. So 0.1 V alphane is typically easily achieved. And this chain of plasmoids and X points is a good source of initiating and sustaining particle acceleration. So there are unstable points which have electric field that can exceed the magnetic field, and that can jumpstart the acceleration of particles. So what determines whether you're relativistic or not? This is this parameter sigma, which we call the magnetization, the ratio of magnetic energy to rest mass energy. So if magnetic energy went into the particles, particles would gain a significant gamma factor if sigma is much larger than 1. So strong magnetization implies relativistic particles. So in that regime, we find that the typically reconnection is very efficient at accelerating particles. So these are results back from about 10 years ago, showing that we've already seen this acceleration in 2 dimensions. So this is a spectra of 2-dimensional reconnection showing quite significant dependence on the magnetization. So for low magnetization, you have steeper spectra. For stronger magnetization, you get harder spectra. This is electron-positron pairs. It can even exceed p to the minus 2, get to something like p to the 1.5. That was the finding from 2-dimensional simulations. The idea for acceleration was shown in this movie by Lorenzo. So particle gets in, gets a kick at the x point, that's its energy. And then the rest of the acceleration is gathered when the particle gets stuck between the plasmoids and gains energy from bouncing around between converging plasmoids and also in the contracting plasmoids. So that leads to particle acceleration in distinct stages, and that has been explained quite nicely in the literature. So what has changed is that it turns out that this picture, while generally okay, has different predictions when you go to 3 dimensions. So in 3D, you see slightly different spectra. And also, you see higher energy particles being created in 3 dimensions. Also, addition of radiative effects creates rather non-intuitive consequences. So strong cooling can actually enhance radiation and enhance acceleration and radiation in these sheets. And also, recent work on adding turbulence with reconnection and radiation creates interesting opportunities for explaining observations. So what's going on? So in 3D, the sheet becomes unstable to both drift kink instability, which is along that direction, but also the tearing mode, which is this formation of the plasmoids. In 2D, these look like organized islands. In 3D, they become these flux ropes. Sometimes they're not completely connected, so they're kind of little blobs flying around. The point is that in 3D, when run with large enough boxes, it is possible for particles to not get stuck in the plasmoids and instead kind of surf around the current sheet. So they can go up and down into what we call upstream and the downstream, where the coherent field is. So in this case, the field is, I believe, like this and like that. So you can see here an orbit of a particle. This is from work by Lorenzo's group, which kind of surfs around this current sheet and sees converging flows towards the current sheet, accelerating to very high energies. And what's shown here is that between 2D and 3D, you get different spectra. So in 2D, the dashed lines, you get steeper spectra than in 3D. What you get is roughly universal gamma to the minus 2 spectrum at high energy. And this is illustrated in more detail here. So there is a 2 dimensions seem to produce very sigma-dependent power law. In 3D, you get more consistent sort of independent power law in sigma. And Lorenzo has nicely explained this result in analytical form. When you go into 3 dimensions and add cooling, another effect happens. So actually, cooling seems to allow you to enhance acceleration, at least for the species that are not cooling. For example, the ions. If you have electron-positron ions simulation, like it was done in this work by Sasha Chernoglazov, Haik, and Sasha Filipov. So you have, this is the uncooled simulation, and this is the cooled simulation. And in this case, the magnetic field goes along this direction. You can see that uncooled simulation produces much fatter plasmoids. The cooled one seems to produce much smaller plasmoids. And it is much easier for particles to not get stuck in the plasmoids and continue accelerating. So in fact, cooling allows some species to get to higher energies and also get flatter spectra. So for example, these are the ion spectra with strong cooling. They're actually able to get to higher energies with flatter spectra. What's also important with cooling is that there is this phenomenon of radiation burn-off, and that radiation burn-off limit predicts that the radiation from a very strongly cooling sheet should not extend beyond about 16 MeV in photon energy, because the particles are gaining energy at the rate that they're losing energy to radiation. It turns out that if you have strong cooling effects, it is possible for particles to find such trajectories where they can exceed this synchrotron burn-off limit because they're surfing and getting accelerated in regions of weaker magnetic field right in the middle of the sheet. So an exciting finding was that you can actually exceed the synchrotron burn-off limit, go above 16 MeV by this ratio of magnetization to the synchrotron cooling gamma, so the gamma where you're accelerating at the rate of your radiation. So this was shown in this plot. So here you can see as you increase the cooling, the cutoff actually moves to higher energy. So this is a bit counterintuitive, but it seems to be quite a robust effect. Okay, so so addition of radiation and reconnection has shown that there is much to be found beyond the simple expectation. So here, the group of Daniel Groschel, Sasha Filipov, Andrei Belovorodov, and Moshotsky went all in and decided to do turbulence with reconnection and cooling, and they found even more than they bargained for. They found shocks. So in this box, they tried to stir a box with a electron and proton plasma, representing the conditions you would expect to see in the corona of the accretion disk. So electrons were strongly cooled, but the protons were just getting energy without cooling. And what they found is that immediately the system relaxed to a 2-temperature state, which is something we expect to see in accretion disks at low accretion rates. So this is the simulation showing the temperature, magnetic field, and the existence of fast waves and the currents and temperature. So this stirring led to intermittent reconnection. So where these strong currents are is where the reconnection happens. And also you see waves flying around, and these waves deepen into shocks. And those shocks can result in extra acceleration. What you see is that the particles not only relax to temperature solution, but they also get a non-thermal power law. So there is a power law of electrons and power law of the ions that is achieved. The peak results in a Compton upscattered peak at around 100 keV, which is very nice for explaining the high energy emission from accreting black holes, such as NGC 4151. The prediction of this work is that there should be a non-thermal tail beyond the MeV range, which is still unprobed by the existing observations, but it's a wonderful prediction to see with upcoming missions. Also, the fact that you have these non-thermal ions created in an accretion disk probably suggests that this could be a source for neutrinos. So these energetic ions colliding with something could produce neutrinos. And that's an interesting idea, because this source is indeed a neutrino source for ice cubes. So that's great. So once you add enough physics and you do plausible initial conditions, things start to fall into place. And we get two temperature solutions and good acceleration and good predictions that seem to match observation. So that's very exciting. And it's a good step showing that these ab initio simulations are actually worth doing and continuing doing. OK, so how am I doing it? OK, so something that we didn't quite expect on reconnection, I just want to throw this out there as a surprise to me, is that so in high sigma reconnection, relativistic reconnection, we have seen this beautiful plasmoid chains forming. And I asked my student to just see what happens if you go to lower sigma. Just go to lower magnetization, just stick with pairs. And we were just interested to see how the acceleration would behave. And what we found was something that we didn't expect. So what we found is that in a simulation of sufficiently large size, the current sheet no longer looked like an island chain. And instead, it looked like something different. It looked like what some people could call Pechek reconnection. So if I run this in time, what you see here is that reconnection does happen. There is the plasmoid chain over here. It's very tiny because it's a very huge box. So over here, you see still, zoom in here, you see still plasmoids happen. But then those plasmoids don't become enormous, all-encompassing plasmoids. Instead, you get this kind of diffuse exhaust separated by sharp jumps in density, temperature, et cetera. And in fact, this looks like the solution that was proposed by Pechek in 1964. And what's happening here is that most of the reconnection happens right around this X point, but then you have this exhaust, which is demarcated by slow shocks. So there is two shocks on both sides, which are a slow mode shock in the plasma. And that's where most of the magnetic field is dying. So the jump conditions at this weak shock, the slow shock, are actually removing the magnetic field. So very interesting thing. We're trying to see this now with electron ions, and it seems to still exist, although it's a bit technically challenging. The main difference between this simulation and what has been done so far is just the size of the simulation. So previous simulations were kind of stopping somewhere around this red box, and it wasn't quite clear what's going on. But if you go just for another factor of 3 to 4 to 5, things become more clear. In a way, it couldn't have been anything else, because mass has to be conserved. And it's very hard to conserve mass in an island chain which has nowhere to go, right? So it had to have a single outflow. And it seems to form it here. Now, the question is, if we go back to a relativistic case, will we recover something like this? If we go for a relativistic case in a very huge box, I'm not sure. But mass conservation is on my side. I think it should do something like that. We'll see. OK, so I'll leave this as a curiosity for now. So let me switch to the next topic, which is acceleration in shocks. And here, just recent progress has been on understanding better the microphysics of the electron and ion injection into the acceleration process. So one of the things about diffusive shock acceleration is that it predicts well, we'll get to that. So it predicts the power law shape, but it doesn't predict the normalization of the power law. It is dependent on the microphysics, and we've studied a lot of the electron and ion injection physics on the microphysical level. The recent finding is that some shocks, which appear completely dead in 2 dimensions, actually get re-energized in 3D. So 3D effects are quite important, particularly in oblique shocks. And also we've encountered what I would call the high Mach number frontier. As we get to Mach numbers that are of relevance to something like a supernova remnant around 100 and above, things become very time dependent, very turbulent, and very interesting. So this is sort of the frontier of what we're trying to do now and trying to address it with multiscale simulations. So let's go in a little bit more detail. So first of all, what is shock acceleration? I don't have to explain it, but I will. So the idea is that a shock is a continuously converging flow. So the upstream and the downstream of the shock are moving at relative velocity to each other. And if a particle manages to bounce between the upstream and the downstream, it will gain energy. Just managing to bounce means that there is some kind of turbulence on which it can scatter. And this turbulence presumably is self-generated. So these particles need to provide their own turbulence. If that happens, kinematics of the bounces and advections through the system predicts a particular power law shape of p to the minus 4 in momentum or e to the minus 2 in relativistic energy. The only thing you're missing is the normalization. So you don't know how many particles are doing that. In fact, it could be 0. So for some shocks, and 0 is in fact 0. But for some, it's actually finite. But in order to find this, you need to kind of solve this whole triangle of shock structure, magnetic turbulence, and particle acceleration, because they're all affecting each other. So the particles that are created at the shock can go in front of it and drive turbulence, and which will affect the shock. So the predictions of DSA, diffusive shock acceleration, is that this self-generated turbulence exists. It results in effective diffusion of particles. And that predicts this universal p to the minus 4 spectrum. It does not predict an injection fraction. And it also predicts the existence of nonlinearity. So if the energy in the cosmic rays is large enough, it will back react onto the flow and will affect this shock structure. So it would be nice if we could see all of these effects. And indeed, we try to verify them with kinetic simulations using both particle and cell and hybrid simulations. So in hybrid, we only evolve the ions as kinetic particles, not electrons as a fluid. In PIG simulations, we do both electrons and ions as kinetic particles. So what we generally find is this kind of phase space of shocks, where on this axis, we plot the 4 velocity of the shock. So these are relativistic shocks. These are non-relativistic shocks. And on this axis, we plot, again, something that looks like the magnetization. In fact, in this case, I a little bit cheated. This is now gamma minus 1. So this is a kinetic energy, not just rest mass energy density. So ratio of magnetic energy density to kinetic energy density in the upstream in front of the shock, measured with respect to the shock. So I call it magnetization. Adults also call it the Alfvénic Mach number, so 1 over ma squared, where Alfvénic Mach number is the ratio of velocity to the Alfvén velocity. You can also rephrase it in more plasma physics terms as the ratio of the skin depth to the Larmor radius of the ions. So if this ratio is large, that means that the magnetization is large. That means that the skin depth is large compared to the Larmor radius. And in that case, you will get, means that the Larmor radius is very small, so the particles will be just gyrating a lot. If it's the other way around, skin depth is small compared to the Larmor radius, then you will potentially experience various instabilities on the way to the shock. Okay, and what's shown here are various objects, such as non-relativistic shocks in supernova remnants, solar wind, and the virials, accretion onto clusters. This is gamma ray burst, AGN jets, and also wind nebulae. So the idea is that for high enough magnetization or low enough Alfvénic Mach number, your shock is mediated by magnetic reflection. So particles just come in and start gyrating in the compressed magnetic field. At low magnetizations, you're mediated by turbulence. And this turbulence is self-generated. It's called the Weibull instability. And then the shock looks more like a filamentary shock. So which shocks accelerate? The two ingredients for acceleration is that the shock should throw some particles back into the upstream, and that's the kind of the injection part. So the shock reflects some particles, let them go back into the upstream, and then as these particles stream away from the shock, they drive waves, and then they can scatter themselves back to return to the shock. So these are the instabilities driven by returning particles going into the upstream. And what determines whether these conditions are satisfied, it depends on the magnetic field obliquity and the strength of the magnetic field. So if the background magnetic field is weak, then in effect, any kind of turbulence you have in front of the shock will be strong turbulence. So delta B over B will be very large because the background field is very small. And in this case, you will have significant scattering, and these shocks are likely to accelerate. If you have a moderate magnetic field, then it depends on how well it's oriented. If it's oriented parallel to the shock normal, we call it a parallel shock. They're typically good for acceleration. If it's oriented perpendicular, they're not very good for acceleration. So just to give you an example, this is our old friend, the Weibull shocks. This is unmagnetized shock showing the density and the magnetic energy. And this is, by definition, a strong turbulence shock. So here, the delta B over B is large because B is 0. What will happen is that this turbulence is driven by the returning particles from the shock. It's counter-streaming instability in electromagnetic version of it. And that drives fluctuation of the magnetic field. And then if a particle can get stuck in these filaments, it will get accelerated, and that's what we see. So these particles get stuck in the filaments. As they swim around, they will gain energy. OK, so that's the usual story. If we increase the magnetic field, if we add some background magnetic field, then inclination of the field would become important. And if the field is sufficiently oblique, then no particles are reflected. This is the phase space showing this is the incoming flow with negative momentum. This is the downstream thermalized, and then nobody is going back upstream. So you don't see any positive particles. So you can kill acceleration. Or if you have magnetic field along the flow, so along the normal, this is a parallel case, then you see some reflected particles going upstream, driving waves, and everything is peachy, and this stuff starts to accelerate. And indeed, that's what we observe. So these are the spectra for unmagnetized shocks, showing about 1% by number, 10% by energy. And this tail develops with time, sort of becoming more and more like a power law. When you add magnetic fields, things can become stuck. So this is 0 degrees, 30 degrees, and then boom, at 45, you're no longer accelerating. What's happening here is that in this case, the particles can't outrun a relativistic shock. They're moving, even if they move at speed of light along some inclined field, they won't be able to outrun a relativistic shock. OK, so for non-relativistic shocks, we have studied both acceleration of ions and electrons separately. And we've reconstructed, we've seen the DSA prediction come true. So this is the slope that the DSA predicts for the ion spectra. We also measured the efficiency of injection versus the Mach number and the inclination of the magnetic field. And you can see that oblique shocks don't accelerate much. As you get closer to parallel shocks, they start getting accelerated. So this is energy efficiency on the order of 10%. For the electrons, and for the simulation where we have both electrons and ion acceleration, electrons develop a power law tail in addition to the ions. This happens for quasi-parallel shocks at sufficiently, well, at least for Mach numbers less than 50, where we have studied this process. So what determines the efficiency of acceleration? What determines this injection physics? That is controlled by the microphysics of the shock. So right at the shock, what you see is this is phase space of incoming ions. They kind of bounce off the shock, start gyrating. And you can see that some particles can gain enough energy through these gyrations that they start outrunning the shock and going back upstream. So these gyrations gain energy through what's known as shock drift acceleration. Particle rides the shock on both sides of it and can gain energy from sampling the electric field around the shock. The efficiency of this process depends on the inclination of the background field. If the field is too inclined, the particle needs to gain more energy in order to outrun the shock, in order to end up going along the field faster than the shock. It needs more of these cycles, and each of those cycles is lossy, so there are fewer particles that end up accelerating. So that's what ion injection is determined by. And but for electrons, what we've done recently is to understand how electrons are injected and how does electron tail connect to the ion tail and how they compared. And it turns out for electrons, despite the preconception in the literature that there should be some kind of pre-acceleration of electrons where they need to gain enough energy to have large Larmor radii to start crossing the shock. What in fact happens is that electrons are very mobile along the field, and they can mirror off the shock and run along the field quite easily. So in fact, the injection condition for electrons is just that they should be just faster than a few times than the shock velocity. So the effective sonic Mach number for electrons has to be less than 3. And that's easily achieved with preheating in front of the shock due to various instabilities that electrons encounter as they approach the shock. So it turns out the electron injection, or at least reflection from the shock, is much simpler than was expected before. And in fact, what we observe is that let's see here. What we observe is that the electron spectrum nicely connects down to the Maxwellian. So there is no extra pre-acceleration physics where they have to gain some energy in order to start outrunning the shock and become like the ions. But so from doing these simulations and actually producing a model that fits these power law tails, we can predict the ratio between electrons and protons, measure this kappa EP parameter, which in our simulations, when extrapolated to realistic mass ratios, we get about 10 to the minus 3 in the ratio, which is consistent with what's observed in the supernova remnants. So, yes? I think it's smaller than that for cosmic rays. That is the cosmic rays, yes. Yeah. Maybe we were measuring, yeah, okay. When?
It's energy dependent, depends on volcano.
Yes.
Okay. It's the same now.
All right, so the conclusion so far is that quasi-parallel shocks accelerate both ions and electrons with efficiency of about 10 to 20% by energy and a few percent by number. And the relative electron to proton ratio is 10 to minus 3 to the minus 2. Quasi-perpendicular shocks, they don't accelerate ions very well, but they do accelerate electrons. For electrons, we have seen efficiency of like 10% in energy, maybe 5% by number. So they're actually quite interesting as electron acceleration sources. But the caveat is that we have seen this mainly happen in 1D, and I don't trust 1D very much. And maximal energy is still an issue because magnetic field needs to be amplified quite significantly. And whether the real systems amplify the field to the values needed is still unclear. So recent progress on this on the front of the going to 3 dimensions was made, breakthrough, I would say, made by Luca Russo and Damiano Caprioli, and recently extended in the common work with Lorenzo Cironi and myself, is that the 3 dimensions seem to affect this turbulence quite significantly. And for oblique shocks, even the ions start to accelerate. So what's shown here is the spectrum of ions in 2D for oblique shock at Mach number 100. And then this shows the spectrum when you go to 3D. So some kind of non-thermal tail starts to develop in 3D because the turbulence structure looks very different in 3D. So this is 2D. In 2D, it does not allow particles to go back upstream. In 3D, the structure becomes more porous, and particles can actually outrun the shock. So that's both promising and scary because that means that we need to run 3D simulations, and they're very expensive. But we'll get there. OK, so all right, so these three checked off. What about nonlinear effects? So for nonlinearities, what we expect is that in order of particle energy, in the order of increasing particle energy, we expect that the magnetic field obliquity will kind of change the reflection from the shock. So more oblique shocks will reflect less. And then if you put more energy into the particles, perhaps they can decelerate the upstream and change the jump conditions at the shock. That's the foundation of the nonlinear DSA theory. We have not seen that clearly in the simulations. And ultimately, another mechanism is shock reformation. So if you put too much energy into the particles, perhaps shocks will jump forward and reform somewhere else. So let me show you a few examples of some of this physics. So these are now larger. This is Mach number 20, and this is Mach number 80. You're seeing the structure of the magnetic field in front of the shock driven by reflected particles. And what you can clearly see is that the waves can get to pretty strong, right? So in this case, delta B over B can get up to 10. This is much smaller in this case. These waves now start to look not like a constant wave, but in fact some kind of a wave train. It comes with sort of amplitude modulation. So these things are called slams, or strong large amplitude magnetic structure. I didn't invent this. This comes from the heliospheric literature. It's actually observed at the Earth bow shock when the ions are outrunning the shock. And so these things starts to form when the particles escape and drive Bell instability, non-resonant instability, which amplifies magnetic field. And these slam structures can get pretty strong close to the shock. And in fact, they can start trapping particles. And we've seen this. So here, some electron orbits get stuck between the shock and the slam and gain significant energy just from these two converging structures colliding together. And this can change the spectrum of electrons close to the shock. So from these bounces between the rock and the hard place, they can actually gain significant energy gain and change the slope of DSA because their escape probabilities are all different now from standard diffusive shock acceleration. So this mechanism can actually lead to steepening of electron power loss that are probably seen in the data. OK, so let me show you something about the future. So the future in this business is going to multiscale simulations because we're resolving we have to resolve very small scales with our particle and cell results, with particle and cell simulation. So we have to somehow be able to sample very large scales in front of the shock for much longer. So how we do that is to simplify simplify our simulations, because most of the time in our PIC simulations is spent evolving thermal particles. So most of the particles are thermal and therefore boring, and they're not very interesting. So what we want to do is to somehow simulate only the interesting ones and not simulate the boring ones. So how do we do that? One way is doing this method called MHD PIC. So this is MHD with cosmic ray particles. So the idea is that you evolve the particles inside of MHD simulations using Lorentz force, where electric and magnetic field comes from MHD. The MHD just does its own thing, except it's affected by the Lorentz force on the cosmic ray. So the negative of that force is pushing on the particle, on the flow, and the energy is also going the other way. So this has now been implemented in Athena and Athena++, and also in Pluto code, and we've been using all three of them for these projects. The idea then is that you can do feedback. So here's an old simulation from 2015 where we were injecting cosmic rays at the shock. at some fixed rate, and you can see strong turbulence develop in front of the shock. The only problem is that if you just keep injecting constant fraction, you can break the whole simulation, because at some point it's not even clear where the shock is. It's now a turbulent mess. So really, the real shocks cannot do that. They must somehow regulate their injection. And what we've tried to do recently is to somehow prescribe a way for the shock to self-inject, and to control how many particles it prefers to inject. So what we do is we, among several prescriptions, is that we inject test particles in front of the shock. So they're just not, they're not doing anything to the flow. They just go through the shock. And the ones that scatter back, just kinematically, they're hot enough to get scattered back. The ones that get scattered, we catch them and we, what I call, promote them. We allow them to start recording current and charge onto the grid, and then they start pushing onto the flow. And this can work. So this is shown here for oblique simulation. So the magnetic field is like that. You can see that some of these test particles get reflected. We start promoting them. They start driving waves. OK, so but does it do any kind of feedback? So this is a simulation in 1D for a Mach 50 shock. So what's shown here, this is the magnetic structures in front of the shock. This is the phase space. So you see XPX. This is XP. And here you can see the spectrum in front of the shock. And this is the spectrum behind the shock, so between these two red lines. So what you see is that DSA starts to work. So you start to develop a downstream power law tail. And also these slams start to develop. And when these slams develop, they start trapping some of the particles. So here's another simulation that is probably right. Here's a higher Mach number simulation, which shows a more vigorous upstream activity. So you start driving stronger wave packets. So these are these slams going towards the shock, which modulate the injection of the returning particles. So in these simulations, there is one free parameter, which is how many test particles do we put in. So the way we control it is we basically say that if we assign some weight to these particles, so if, let's say, all of them get promoted, some fraction of the mass will go into the cosmic rays. And what's interesting about this is that what we find is as we change this fraction, as we change the theoretical maximum amount of mass we can put into these cosmic rays, the shock actually doesn't care. It seems to find a solution where it doesn't care how many particles we give it. So what you see here is different levels of what we call injection, so different weight of the test particles, going all the way to 3% from 0.5%. And what you see here is the spectra. The spectra seem to kind of saturate. So the non-thermal part of the distribution seems to saturate. The thermal part, of course, it depends on our injection, because there's more green particles than red particles. But the returning ones seem to saturate at some magic value. What that magic value is effectively it tries to control how much charge it's putting in front of the shock. If it's putting too much charge, the waves will grow stronger. They will trap more particles, and they will contain the injection. So it looks like for some range of parameters, these shocks are sort of reaching self-regulation. So they're trying to put in only as many particles as is required to maintain some kind of constraint. And that constraint is probably just how much charge it's trying to keep in front of the shock. So that means that perhaps there is a hypothesis here that perhaps there are two kinds of shocks. So one type is what I would call the weak shocks, where the injection is controlled by the upstream magnetization. So these shocks are probably have smaller delta B over B in front of the shock, maybe Mach numbers below, say, 80 or something like this, maybe below 50. These shocks will be controlled by the inclination of the field. But then at higher Mach numbers, you will be in what we'll call the strong shock regime, where the turbulence will regulate how much injection happens. So the microphysics that we so love at the shock is very important, but it's important locally. The global shock structure will figure out how to make it work effectively. So the turbulence will control how much the shock is allowed to inject. Okay, I'm almost at the end. So our final thing that I wanted to mention is this idea of system modeling. So here a few works have been done by the collaboration, such as the hierarchical accretion shock. So this is trying to explain the ultra-high energy cosmic rays production. And the idea by the Stanford group and the Naomi's group is that the shocks, the particle acceleration up to ultra-high energy starts from the supernova remnants, proceeds into the winds of the galaxies, and then into the shocks surrounding the galaxy structures, the filaments. And these hierarchical shocks can reaccelerate particles and create the ultra-high energy cosmic ray that we see. So to do this properly, one needs to understand how shocks accelerate particles, how much magnetic field exists in front of the shock. So this is a very interesting idea that could be coupled to the machinery that we've developed from the first principal simulations from shocks. Then there are ideas on how to model GRB afterglows, which I won't talk about, the jetted TDEs and the cosmic ray transport. All of this is happening in the collaboration. And then here the talk on Saturday about merging neutron star modeling from Jasmine Parsons. And the work that I've just described on black hole jets and Caroni. And there's more work, of course, from Bort Ruperto's group. So all of these have to include the prescriptions for particle acceleration. And our goal as a collaboration is to provide the right prescriptions to fit into these global system modeling of the particle, of the astrophysical sources. OK, so I'll leave my conclusions here. We've made some progress, and there's more things to be done. Thank you.